An integer p is called even if p can be written in this form: p equals 2m for some integer m. Similarly, an integer p is called odd if p equals 2m plus 1 for some integer m. Proposition: let p be an integer. If p is even, then p squared is also even. If p is odd, then p squared is also odd. Let's see the proof of the first statement, A. Suppose p is an even integer, p equals 2m for some integer m. Then p squared is given by 4m squared, which can be written as 2 times 2m squared, or 2 times n, where n is 2m squared. So it shows that p squared is also an even integer. Let's see the proof of B. Let p be an odd integer, then p can be assumed to be equal to 2m plus 1 for some integer m. Then p squared is given by 4m squared plus 4m plus 1, which can be written as 2 times 2m squared plus 2m plus 1, or 2n plus 1, where this quantity is n. So this shows that p squared is an odd integer. The next proposition: there exists no element r in Q such that r squared equals 2. In other words, no rational number squares to 2. Let's see the proof. Let us assume, on the contrary, that r is a rational number of the form p over q, where p and q are integers that are not both even. Then we can write p squared over q squared equals 2, obtained by substituting by r equals p over q into the equation. Or p squared equals 2q squared. Now this shows that p squared is even, since p squared equals 2 times some integer. This implies p must also be even, because if p is odd, then so is p squared. Let p equals 2m for some integer m. Then the previous equation gives, namely, p squared equals 2q squared gives this equation: 4m squared equals 2q squared. Cancelling the common factor of 2 and reorganizing the terms, we obtain q squared equals 2m squared. Now this shows that q squared must also be even, and so is q. But this contradicts our assumption that p and q are not both even. We started our proof with the assumption that p and q are integers but not both even. This contradiction proves the assertion that r cannot be a rational number whose square equals 2. Order on a set. Let S be a set. An order on the set S is a relation denoted by this symbol with the following properties. 1. If X is in S and Y is in S, then one and only one of the following statements hold true. Either X is smaller than Y, or X is equal to Y, or Y is smaller than X. Property 2. If X, Y, and Z are in S with X is smaller than Y and Y is smaller than Z, then X is smaller than Z. It is often convenient to write Y larger than X in place of X smaller than Y. The notation X smaller or equal to Y indicates that X is smaller than Y or X is equal to Y, without specifying which of these two is to hold. In other words, X is smaller or equal to Y is the negation of the statement that X is larger than Y. Ordered set. An ordered set is a set in which an order is defined. For example, the set of rational numbers is an ordered set, because every two rational numbers, R and S, is either smaller than R is smaller than S, or R is equal to S, or R is larger than S. And if we have three rational numbers, R, S, and T, such that R is smaller than S and S is smaller than T, then R would be smaller than T. So Q is an example of an ordered set. Bounded set. Suppose S is an ordered set and E is some subset of S. If there exists an element beta in S such that X is smaller or equal to beta for all X in E, we say that E is bounded above and call beta is an upper bound of E. In short, if every element X of E is smaller or equal to some element beta in S, then we say the set E is bounded above and beta is an upper bound. Lower bounds are defined in a similar way. Instead of less or equal, in that definition, we need to use larger or equal. Let's look at an example. Suppose A is a set with these elements, or A contains the elements of the form 1 minus 1 over n, where n is a natural number. For example, if we substitute n equals 0, 1, we get 0. N equals 2, we get a half. N equals 3, we get a 2/3, and so on. Clearly, A is bounded below for any real number R smaller or equal 0, and bounded above by any real number S larger or equal to 1. For example, 0 is a lower bound of the set A. -1 is also a lower bound of the set A. So any real number smaller or equal to 0 is an lower bound of the set A. In a similar way, 1 is an upper bound of A, 1.5 is an upper bound A, 10 is an upper bound of the set A. So we see that lower bounds or upper bounds are not unique. Let's look at another example. Consider the set B of rationals which are positive whose squares are less than 2. For example, the rational number 1 is in B. Because it is rational, it is positive and its square is smaller than 2. Similarly, the rational number 4/3 is also in B. Because this is positive and its square is 16/9, which is smaller than 2. But the rational number 3/2 is not in B because its square is 9/4, which is not smaller than 2. Similarly, the number 2 is not in B also. Clearly, the set B is bounded below by any real number r smaller or equal to 0, and it is bounded above by any real number s larger or equal to 2. However, it is not clear at this moment whether B has any largest or maximum element in it. By a largest or maximum, we mean an element alpha in B such that x is smaller or equal to alpha for all x in B. In short, by a largest or maximum element of a set, we mean an element alpha in B such that all the elements is either smaller or up to equal to alpha. Least upper bound. Suppose S is an ordered set, E is some subset of S, and E is bounded above. Suppose there exists an element alpha in S with the following two properties. 1. Alpha is an upper bound of E. And 2. If gamma is smaller than alpha, then gamma is not an upper bound E. Then alpha is called the least upper bound of E. Since alpha is an upper bound and no element smaller than alpha is an upper bound, so alpha is called the least upper bound of E, or the supremum of E. And we write alpha equals sup E. Sup stands for supremum of the set E. Note that alpha, if it exists, is unique. The greatest lower bound, or infimum, of a non-empty set E is defined similarly. So the infimum of a set E is denoted by inf E. The supremum or least upper bound property of a set. An ordered set S is said to have a least upper bound property if the following is true. If E is some subset of S and E is non-empty and E is bounded above, then supremum of E exists in S. In short, an ordered set S is said to have a least upper bound property if every non-empty bounded above subset of S has supremum in S. For example, the set Q does not have the least upper bound property because the non-empty set E, which contains all the positive rationals whose square is smaller than 2, The supremum doesn't exist in Q. Let's look at the example A again. We saw that the set A is bounded below by any real number R smaller or equal to 0. And it is bounded above by any real number S larger or equal to 1. And it is clear that the number 0 in A is the smallest number in this set. So the infimum of A is 0. Because any number larger than 0 cannot be a lower bound, because there is a 0 smaller than that. But it is not clear, even from the figure, that this set has any maximum element in it. 1 is an upper bound, but 1 is not in A. This can be proved from here. For no value of n, this would become exactly equal to 1. But the numbers seems to getting closer and closer to 1. We might think that there is a number close to 1 at which all the numbers of this set stops. In other words, there is a number beta such that all the elements of this set A is smaller or equal to beta. But we will prove later that no matter how close the number beta is to the number 1, there would be some number, some element, 1 minus 1 over n in this set, which exceeds beta. So the set has no least upper bound. Let's look at another example. Suppose B is a set of rationals where R is positive and its square is smaller than 2. Earlier, we saw that B is bounded below by any real number R smaller than or equal to 0 and bounded above by any real number S larger or equal to 2. It was not clear that if B has any maximum element in B. We will prove that B has no largest or maximum element in B. To prove this, let's take an element P in B and define another rational number Q by this formula. So Q equals P minus P squared minus 2 over P plus 2. If we do the algebra in the right hand side, it takes the form 2P plus 2 over P plus 2. A simple algebra gives that Q squared minus 2 equals 2 times P squared minus 2 all over P plus 2 all squared. You just need to square Q and subtract 2 from it. So it will give us 2P plus 2, P plus 2 all squared minus 2. And this will give us this expression. By equation 2, we see that Q is positive. And since P squared is smaller than 2, by equation 3, we see that P squared is also smaller than 2. Since P squared minus 2 is smaller than 0, so this is the negative quantity. Therefore, Q squared minus 2 is negative. which shows that q squared must be smaller than 2. Therefore, q must be in the set B. Also, by equation 1, we see that q must be larger than p. Since equation 1 gives q minus p equals negative of p squared minus 2 over p plus 2. Since the numerator p squared minus 2 is negative, and the negative of a negative is just a positive quantity. So q minus p is larger than 0, or q must be greater than p. We have this. Thus, we defined a rational number q based on p only, which is larger than p, but still in the set B. Thus, the set B has no maximum element in B. Let's take a p-value 1 from the set B. If we substitute the p-value 1 into the equation 2, we get the q value 4/3. And if we take this 4/3 as p-value, and if we substitute it in the equation 2, we obtain q value 7/5. Similarly, if we take 7/5 as the p-value, we get q as 24/17. And so on. These numbers are called the rational approximations of square root of 2. So no rationals squares to 2, but these rational numbers are getting closer and closer to a number called square root of 2. Similarly, if we consider the set of rationals where r is positive and its square is larger than 2, now we are considering all possible rationals whose square is larger than 2. This set has also no minimum or smallest element in it. Suppose we start with an element in this set. 2 is there because 2 is rational, 2 is positive, and its square is larger than 2. And if we substitute into the equation 2, namely q equals p minus p squared minus 2 over p plus 2, we obtain 3/2. Then if we take 3/2 as the p-value, then we obtain q as 10/7. And then we substitute 10/7, we get 17/12, and so on. These numbers are also called the rational approximations of square root of 2.